Okay, we're going to move on to chapter 3, which is about forced oscillation, non-periodic and sinusoids. If you remember in chapter 2, last week and the week before last, we were finding solutions to forced systems, but we weren't looking at the transient solutions. We were just looking at the solution as time goes to infinity. We were not worrying about what's going on to start with. Well, here we're going to look at what goes on to start with, because the solution is actually going to be a little bit more complicated than what we found before. So we're going to talk about the general approach that we take to start with. Then we're going to look at non-periodic excitation. So this will be things like rectangular functions and functions that grow with respect to time. We're going to look at some exponentials, decaying exponentials, and then we're going to also look at periodic excitation, so things like sinusoids and offset sinusoids. We'll then discuss damp response, because I'm going to start off talking about the non-damp case because it's easier, and then I'm just going to introduce the idea of this thing called beating, or the beating phenomenon, which I'll show you an example of as well. And then we'll probably have a go at doing one of the exercises at the end of the chapter. So the approach we take in this chapter, if we haven't, this is obviously a damp system, so there's a mistake already there, okay. Ft is the function of the excitation force. Now if we were to solve this differential equation, there's a way to solve it where you have to find two solutions. One is called the complementary function, XCF, and the other one is called the particular integral. Okay? And these help deal with each part of the solution. XPI is what we found before, and that's the solution as time goes to infinity. After that, oscillation will die away after your initial natural oscillation. Whereas XCF is the thing that deals with the transients. XCF is the solution to the homogeneous form of that equation. Homogeneous means that Ft is 0. So in fact, XCF is the solution to the free function, or the free system, and XPI is the solution to the forced one. And basically, since they're linear systems, you can just add them together to get the complete solution. That's the approach that we take. So in the case of an undamped system, this is the solution that we found to the XPI bit.
Obviously here I meant to say XCF.
And we found that that solution works as long as omega naught is root k upon m, and A1 is A cosine phi, and A2 is A minus A sine phi. That's from chapter 2. In the case of a damped system, you have very much a similar equation, except you have this exponential term in here, e to the minus zeta omega naught t, because it's a decaying exponential. It's got damping involved, so the whole oscillation will decay. And these are the solutions, so this one and this one are the solutions for that XCF, the complementary function. This is what the system will do if the whole thing is unforced. Okay? You have this one and this one. Okay? Here, omega naught is the same thing, root k upon m. Omega d, damped angular frequency, is omega naught times 1 minus zeta squared, square rooted. And then you have the same terms for A1 and A2, A cosine phi and minus sine phi. In fact, sorry, these again, these should be alpha, because that's the alpha term up there. So that's XCF for both of those damped and undamped systems. And they will be the same irrespective of what the forcing function will be. Okay, they do not change. The forcing function has no effect on what the unforced response is going to look like. Okay, so your solution will always include either this equation at the top, or if there's damping involved, it'll include this equation at the top. It'll always include them. Okay, we don't need to worry about solving them. We did that in chapter 2. Okay, so in a sense, this bit is actually quite easy because you just take these answers from chapter 2. The more challenging bit is to find this thing called the particular integral, the thing as time goes to infinity. And unfortunately, it involves a rather crude method of trial and error. Essentially, what we've got is a table here. This table is in your notes. And you look at the forcing function and decide what form the forcing function takes. And so if your forcing function is a constant, you take the trial solution being a constant. Here, the Greek letters in this side of the graph are basically constants, arbitrary constants that we will find as part of the solution. So don't worry about the fact they're Greek. And notice also that the gamma term here, in this line and this line, that's not the same as C upon M, okay, which we had last week. It's just an arbitrary constant. So if the forcing function is a constant, you take a constant as your trial solution. If it's a polynomial in terms of t, so it's something that changes with respect to time in the form of a polynomial, then you take a polynomial in t of degree r. Okay? So if we have a polynomial in terms of t squared, then obviously you have a alpha t squared plus beta t plus gamma as your trial solution. If you have a sinusoid, then you take this form of the sinusoid. Remember back in chapter 2 when we solved for the sinusoid, we had a cosine omega t plus some phase. And then also in chapter 2 we said that, well, that can be shown to be something that looks like this, where you have two constants instead. So that a cosine or sine, you can take both of those. And then obviously if you've got an exponential as your forcing function, then you take an exponential as your trial solution. So it's relatively straightforward, although it's a relatively crude method of trial and error. With a bit of knowledge, this table, you can work it out, because basically the forcing function will give you an indication of what the trial solution should look like. And the reason that works is that because, as we said back in last week or the week before last, if you start forcing a system with a forcing function that you impose, eventually that system is going to follow what you impose. Though, like I said, what happens at the beginning with a real system with damping, that's going to die away. And you end up imposing what you're going to impose. So obviously the solution is going to match up with the forcing function-ish, with a different amplitude and some different variables. But we'll see. Let's see what happens. So the first function that we're going to deal with is a rectangular step forcing function. Okay? So as time increases, at time equals 0, we apply a constant force of F0. And then obviously as time goes off to infinity, we keep applying that force. So, the equation of motion. Like I said, we're dealing with undamped systems to start with. We'll deal with damping later on. We have mx double dot plus kx equals F0. F0 being a force, which is a constant. The complementary function for the undamped case is this, as we saw before, and that doesn't change. A1 and A2 will find. Let's not worry about that for the time being. So that's XCF. We need to find XPI. Since the forcing function is a constant, we try XPI as a constant. And that constant I'm going to give the name gamma. It could be called whatever you want, but gamma I'm going to give it. And so to insert it into our equation of motion, we must take the derivative of gamma with respect to time and the second derivative with gamma with respect to time, because we have an x double dot term in our equation of motion. So if xpi is gamma, then x dot pi, obviously the derivative of a constant is 0, and obviously the derivative of 0 with respect to time is also 0. So x dot double dot pi is 0, We stick that into our equation of motion, so x double dot is 0, x is gamma, and so we end up with f equals k times by gamma. So we can solve for gamma, that's simply f naught upon k, which is our particular integral. So if our solution, the complete solution, this is the complete solution including the transient and the solution as time goes to infinity, it's simply our XCF, which is our free solution, plus a constant. Our free solution plus a constant. Now we know that this bit, XCF, is simply an oscillation, don't we? Yeah, we found the solution in chapter 1 of that. In that case, if you set a free system oscillating, it's just going to oscillate with the centre at 0. Okay, it's going to oscillate about the equilibrium position. Well, if you apply a constant force to that, the thing's going to oscillate, but instead of being around 0, it's going to oscillate around a constant force. Well, that happens to be our constant force, the displacement of that constant force. And that makes sense. If we imagine that omega is so small that it takes forever for it to do, then obviously the thing's going to sit at that constant force, and that's f naught upon k. Amplitude is a, and you have f naught equals ka or kx. It's the same equation. So that's the general solution, and general because we don't know what A1 and A2 are. And that's because we don't know what the initial conditions are. So to find A1 and A2, we must know what's happening when time is 0. And generally, we can give what's known as rest conditions, as in the system isn't moving at time equals 0, and it's not moved from its equilibrium position when time is 0. Okay, so x at time is 0, displacement is at time 0 is 0, and the velocity at time is 0 is also 0. So these two things, this is a typical initial condition. There may be other types of initial conditions, and there's a question as part of chapter 3 where these are not 0 and you have to find the solution. So what we've got to do is we take our solution, which we had, we have to differentiate it because we've got a value for x dot naught. And so with this, the first term, the omega naught comes out, and then obviously the cosine changes to a minus sign. And with the other term, the omega naught comes out and the sign changes to a cosine, which is where that comes from. F naught upon k, which is in the solution, obviously that's a constant. You take the derivative of a constant, you get 0. So that disappears. And so we apply our initial conditions, x of naught. Well, sine of naught is 0. Sorry, yeah, cosine of naught is 0. So, excuse me, cosine of 0 is 1. And so in the first equation, the non-derived one, we had a1 because it was cosine omega t. Obviously omega t is 0. So cosine of 0 is 1, so we end up with a1. Sine, which is in the second term, sine of 0 is 0, so a2 disappears. And then we've got the f naught upon k term. And so we can easily see that a1 is minus f naught upon k. If we apply 0 to this equation, obviously the sine of 0 becomes 0, so a1 disappears. Cosine of 0 becomes 1, so we end up with a a2 omega naught term. And that equals 0 because there's nothing else, and so a2 must be 0 because omega naught, the natural frequency, cannot be 0. Okay? So a2 is 0, and so you can plug those two values for a1 and a2 in, and you end up with the solution. And that's for the case where you've got initial conditions at rest, initial rest conditions. So x equals f naught upon k times by 1 minus cosine omega naught t. Now what I'm going to do is I'm going to plot that on the board so you can see how we get there.
As it happens, you can't really see on the board what's going on, so I'm going to skip this part in the video.
So as you can see, you've got a 2 times f naught upon k as your maximum the oscillation is centered upon F0 upon K. And obviously we're starting at 0 because there's no force being applied at time equals 0. Okay, is that clear? Linearly increasing forcing function. So here, instead of the forcing function being just a constant force, F0, here we've got some force times by time. So the thing's going to increase as time goes up, okay? It's a linearly increasing function. Now Ft is a polynomial in terms of time. Okay, it's a very simple polynomial. In this case, it's the equation of a straight line. But I could equally give you a cubic or a quadratic, something to the power of t to the 3 or t to the 2, okay, which would also be a polynomial. Here I've just given you a t, but it's up to you. But like I said, it's a very simple polynomial. And there's the equation of motion, mx double dot plus kx equals f times t. So we look at our table and we decide, okay, well, what's the trial function for this solution going to be? Well, we look at the table and we see that this is a polynomial, so we apply a polynomial. Now, we had ft, didn't we? And you think, well, let's just apply alpha t. But the thing is that you can't forget the t to the naught term because in this polynomial. So that's why there's a beta term here. Obviously, if your forcing function was ft squared, you can't just apply alpha t squared as your trial function. You need to have the t to the 2 term, t to the 1 term, and t to the 0 term. So it would be alpha t squared plus beta t plus gamma, or whatever, whatever those Greek letters are. So here we've got ft, so we choose t to the 1 as the first term. Differentiate that, well, alpha t obviously becomes alpha because t disappears, and then the beta is a constant, so that disappears for this solution. And obviously this is a constant, so when you differentiate that, you get 0. Plug them into the equation. X double dot was 0, and then for k we've got alpha t plus beta. And if you group to the t to the 1 terms, so k alpha t equals ft, well, you end up with f upon k, alpha, and beta is 0, just so happens to be 0. And so we can stick that back into the solution and we end up with xpi is f0 upon k, because we had alpha t plus beta, which was 0. So you end up with ft upon k as your solution, as xpi. So as time goes to infinity, that forcing function is basically just going to increase that displacement in line with the force going up. Okay? xpi is that's the thing as the solution as time goes to infinity. At time equals 0, obviously the thing is going to sit at 0, and as you increase the force being applied, basically that force is just going to increase in line with ft upon k. Which makes sense. So if you apply that to the general solution, we've got our xcf here, a1 cosine omega naught t plus a2 sine omega naught t plus ft upon k. That's the general solution. To find the exact solution, we must apply initial conditions. So we'll apply the same initial conditions, 0 displacement and 0 velocity at t equals 0. And so we've got to take this, we've got to differentiate it with respect to time. Now the difference this time, we've got the same things for these first 2 terms, but because we had a t up there, you differentiate it, you just get the constant out, f upon k. So it's slightly different from the solution we had previously. And now we've got 2 equations and 2 unknowns, a1 and a2. Okay, and when t is 0, this equals 0. And when t is 0, the equation at the top also equals 0. And so you go through applying the initial conditions. When time is 0, displacement is also 0. You end up with a1 equals 0. That makes sense if you look at the equation. Cosine of 0 is 1. Sine of 0 is 0. And f upon k times by 0 is also 0. So you just end up with a1 equals 0. Okay, so that's where that comes from. And then in this equation, when t is 0, this term drops out, that's gone. Omega t here is 0, so cosine of that becomes 1. So you end up with a2 omega 0. And obviously you end up with f upon k. There's no t term, so that stays as f upon k. So you end up with a2 omega 0 plus f divided by k equals 0. So a2 must equal minus f upon k omega. So you stick them into the solution for a1 and a2 and you end up with this term as your oscillation. We have an oscillation that's moving up and down, that's increasing as time goes up. Okay, and that makes sense. Essentially it's a forcing function and the oscillation is going to increase as time goes up to infinity. I haven't done a graph of that response. Okay, what about an exponentially decaying force? Here f equals f0 e to the minus t over tau. T over tau, where tau is the decay time in a sense. When t equals tau, the response would have dropped by an amount of e. Okay, because you have e to the minus 1. So our trial solution takes the same form, alpha e to the minus t upon tau. Okay, we take the same exponential, t upon minus t upon tau, but we stick a different constant in front of it because we're not sure what that constant could be. You take the derivative of that, okay, well you get a minus tau, minus 1 upon tau out. So we have minus alpha upon tau times by e minus t upon tau. And you do it again, you get another minus tau, 1 upon tau out. So you end up with alpha divided by tau squared times e minus t upon tau. Like I said, taking the derivatives of exponentials is easy, which is why we use that complex form. So we stick that in our equation of motion. This time, obviously, we employ the x double dot term because that had a value. You end up with this equation. And from that, you can solve for alpha because there's only one term, alpha, in there, one equation, one unknown. You can solve for it just by rearranging the equation. You end up with that rather ugly equation. Fractions in fractions. It's always not nice. And so the particular integral is basically we stick that term, alpha, in front of our exponential, which is what we had as our trial function. And so the general solution, xcf, is the same, plus our xpi. And again, we have to find the derivative to go and solve for initial conditions. In this case, the same case, initial conditions of rest, when x naught is 0 and x dot naught is 0. That does the same thing when we take the derivative here. Again, when you take this derivative with respect to time, a minus 1 upon tau comes out, so you end up with this becoming tau instead of a tau squared, and then you have a tau on the bottom because you have minus 1 upon tau in front of that whole fraction. This is the ugliest solution, to be fair. We stick in t equals 0 for displacement. We have a1, and then you have e to the minus 0 upon tau. Well, that's e to the 0, which is 1. So we end up with a1 plus f0 upon m divided by tau squared plus k as a, okay, so that's the first bit. When this is 0, when t is 0 in this equation, that obviously drops out. A2 times by omega times by 1 minus that lot, because obviously that becomes 0 here. So we have A1 equals minus F0 upon m divided by tau squared plus k. And then A2 is the same thing, except we've got an omega tau times by that quantity. 1 over omega tau. And so we can stick that into the solution. A2, remember, was a cosine, sorry, was sine omega naught t. And then A1 was minus that. And then obviously you've got that times that as the XPI bit. So that's the solution for the decaying exponential. You can make a simplification if you wanted to. This is just in the notes. If you know that obviously omega naught is root k upon m, then you can make the substitution of it in terms of omega naught squared and omega naught instead. Notice the interesting thing about this. What happens when tau becomes so large that the decay time is very slow? Well, what happens, if you think about it, you've got F0 upon 1 plus 1 over something approaching infinity. When anything 1 over something approaching infinity becomes 0. So we have F0 upon k times by 1. The sine omega naught t over omega naught tau, well, again, that tau is on the denominator. As that approaches infinity, that whole term becomes 0. Minus cosine omega naught t plus e times 1 over 0. Sorry, e to the power of 0. Because obviously t upon tau, as tau approaches infinity, t upon tau becomes 0. So we have F0 upon k times by minus cosine omega naught plus 1. What's exactly what we had for the rectangular forcing function. F0 upon k times by 1 minus cosine omega naught t. And that makes sense. If you think about the decaying exponential, if the decay time is so slow that it looks like a rectangle to start with, then obviously you're going to get the same solution as the rectangular forcing function. Now the last form, I'm not going to go through the solution to, but it's called the blast function. And the reason I'm not going to go through the solution of it is it's essentially two functions that we've already solved. This function is formed by the combination of two decaying exponentials, or in fact one decaying and one increasing exponential. You start off at 0, it increases and then dies away exponentially. It's called the blast function because it's the sort of function you might get with an explosion. You get an increase in force that then dies away. So from before, you solve for x1. So that's the function from before. We've got a tau 1 here. And then this is the other one. You've got a minus sign, and you have a tau 2 here. And basically, to find the complete solution, you just add them together. It's a linear system. So you can what's known as superpose the solutions together. You just basically add them to each other. And that's for the case when displacement and velocity are 0 when time is 0. So those are the non-periodic functions. We had rectangular forcing function, linearly increasing forcing function, decaying exponential, and this blast loading, which is a decaying and an increasing exponential combined together. And for each of those cases, we found the general solution, and we found the complete solution when you have initial rest conditions, or initial rest conditions. Now, one of the reasons we're learning about this is that in chapter 4, which we're going to cover next week, or certainly start covering next week, I believe it's chapter 4. No, in fact, it's not chapter 4. It's probably chapter 5. No? No, in fact, it's chapter 6 is when we're going to cover. Basically, chapter 6, we're going to look at a method that applies to multiple degrees of freedom. that uses these solutions as part of the answers to those questions. Okay, so that's one of the reasons we're looking at it. The other reason is obviously this applies to what we were looking at last week as well, single degrees of freedom. What about periodic functions like the sinusoid? Well, we actually solved back in chapter 2 the solution to this. I think chapter 2 we actually said cosine omega t, but remember that was also the solution when time goes to infinity. We ignored the complementary function bit. This time we're looking for the complete solution, including that complementary function, so we can go through the same approach. mx double dot plus kx equals f naught sine omega naught omega t. Now remember, this here is the frequency of which I'm posed by that force. It's not the natural frequency of the system, so there's a difference. There's no subscript of 0 in here. So there's our solution. The complementary function is the same thing, okay, which we saw before. That doesn't change as before. This time the trial solution is that combination of cosine and sine. Okay, basically we know that the thing is going to oscillate in an oscillation, in a sinusoidal fashion, because that's our forcing function. And in this case, omega naught does not equal omega 0. In your notes, I've put in a section when those two things equal, because the solution that we're about to find doesn't apply for when those two things are equal to each other. Okay, I've not put it on the slides. There's lots of maths involved, but it is in your notes if you want to refer to it. So we find the second derivative of this. What happens is that we have a minus omega squared come out from both of these things. So we have minus omega squared times by x, okay, is x double dot. And so you stick that in your equation of motion. You end up with this really quite ugly equation. We have mx double dot, so we have m times by minus omega squared times by x plus kx equals f naught sine omega t. And what you can do is you can simplify things out, okay? If you take k minus m omega squared from the left-hand side and divide the equation by that, you end up with this term here. And this is the point where we got to in chapter 2. We ended up with that the amplitude being f naught divided by k minus m omega squared. If you remember in chapter 2, that was the solution for the amplitude. But here we've got to find alpha and beta. And it's quite clear, if you group the sine terms together and the cosine terms together, you end up with beta becoming f naught times by k minus omega squared. Okay? There's no cosine term on the right hand side, so obviously alpha must be 0, but there is the sine term, so beta must equal that term. And so that solution for xpi is that f naught upon k minus m omega squared times first sine omega t. And like I said, that's what we had back in chapter 2. I think chapter 2 we used cosine omega t as our forcing function, but it's exactly the same. But this time we've got that complementary function stuff to start with as well. And we'll apply initial conditions to find a1 and a2. You do the same thing, you take the derivative. Obviously sine becomes cosine, and the omega pops out, which is why there's an omega up here. And obviously those two terms we've seen the derivatives of before. When t is 0, cosine omega times 0 is 1, so we have an a1 term. Sine omega 0 is 0, so that drops out. And the same thing happens with that term. So we have a1 must be 0. And you do the same thing for the velocity. Sine of 0 is 0, cosine of 0 is 1, and then obviously the xpi bit had a cosine omega t term, so that becomes 1. So you end up with this equation, and you can find a solution for a2, and you end up with this funny thing over here. You plug them into the solution, and you end up with this equation. So notice we've got some amplitude, which we found in chapter 2, times by the sinusoid that you're applying, minus by a sinusoid that's oscillating at the natural frequency, multiplied by a ratio of the two amplitudes. And you can see why this equation doesn't apply when omega equals omega naught, because you'd have sine omega naught times by t minus 1 times by sine omega naught times by t. So there'd be no oscillation, which doesn't make sense. There will be an oscillation. So this doesn't apply when omega equals omega naught. So there's just one more case I want to look at, and that's known as the offset sinusoid. So I bump along before time gets to 0 at 0 force, then suddenly apply a sinusoid and a step function as well, and a rectangular step forcing function. And so this time we've got two, guys, I'll give you a break in just a sec, okay? This time we've got two forcing functions, f0 plus f1 sine omega t. Okay, so bump along, get to time 0, suddenly we've got a step forcing function up to f0 and an oscillation where the peak to peak value is 2 times f1. Okay, so that's what's going on, that's the force being applied. How do we solve for it? Well, it's easy. We know the solution for when the forcing function is a constant, so you take that solution. And you know the solution when you've got a sinusoidal forcing function. We've just found it. And so to get the complete solution, you just add the two together. It's a linear system, so you can superpose these solutions together, i.e. sum them. And so there's our solution for the constant force, which we found. And there's our solution for the sinusoidal force, which we found. So there's the solution. We don't need to worry about having to solve for each of those bits individually and working out multiple values of A1 and A2 and all sorts of stuff. You'll end up with the same stuff. Okay? So that's the answer to that particular case. We're going to look at the damped response. All the previous examples that we looked at was the undamped case, which is our equation of motion had no damping at all. It was mx double dot plus kx equals our forcing function. Well, now we're just going to look at the damped situation. So in the damped case, we had mx double dot plus cx dot plus kx equals f. This is a damped situation. We've got a c term. And we know that our complementary function has that exponential because basically the oscillation, the natural oscillation when you release it with no force is going to die away. And that's obviously what happens. As t goes up, this term becomes closer and closer to 0. And so you end up with XCF becoming 0. Now it just so happens if we do an example, rectangular forcing function, XPI, we do exactly the same process and we end up with the same term for XPI, F0 upon K, because obviously what's happening initially and to do with the complementary function has no effect on the particular integral. And so our solution is our complementary function, which we found in chapter 2, the decaying exponential times by the sinusoidal plus that constant term, f0 upon k. If you apply initial conditions, you end up with a1 equal minus f0 upon k and a2 is 0. The same solutions we found previously. And that's because the only difference between this solution, the complementary function for the damped case, and the non-damped case is the fact that you have omega d in the sinusoid because the frequency is slightly different, and you have a decaying exponential out in front which decays the whole lot. Now when t is 0, e to the power of 0 is 1. So the solution is in fact identical except you've got omega d instead of omega naught. So a1 becomes minus f0 upon k and a2 becomes 0. And if you stick that into the solution, you end up with this solution, which looks very similar to the case when we had no damping. The only thing is that term, that sinusoidal term, decays as time goes to infinity, which makes sense. Yeah? The previous solution we had for the rectangular forcing function is that term there was 1. And so you had a sinusoid that continued on until time got to infinity. Well, this time, as time goes to infinity, this term becomes 0, the sinusoid disappears, which makes sense. If you start something oscillating with a constant force, it's going to move up, oscillate around that equilibrium position, and that oscillation is going to die away. Yeah? Because there's damping in the system. And so if we were to plot that, you end up with something that looks like what we drew on the board, but this time the oscillation is going to gradually reduce, and the frequency of oscillation is the damped angular natural frequency, not the natural angular frequency. The omega d, not omega n. So you end up with this equation as this solution as your thing. But everything else is the same. You have the same, the same constant around which it oscillates. And obviously, if there was no damping, then it would oscillate up to 2 f0 upon k and down to 0. But because it's damping, that amplitude reduces as time goes off to infinity. Now, there's one thing that I want to talk about, which is called the beating phenomenon, which is what happens when omega and omega naught, so this is looking at that sinusoidal forcing function, when they are close but not equal to each other. And so this is a solution we found. Now, when omega and omega naught are close but not quite equal to each other, you have a sine omega t and a minus sine omega 0 t, okay, and that second term is multiplied by virtually 1, not 1 but virtually 1. But because those frequencies are just slightly out, what happens is at some points they add together and they're in phase, but at some points they're out of phase by 180 degrees, in which case you have something minus something, something minus itself, which equals 0. And so you get what's known as the beating effect. And I'm going to demonstrate this to you in a second. Basically, you get phase drift occurring. Sometimes those two sinusoids reinforce each other, but sometimes they actually cancel each other out. And you end up with this thing called beating. Now, to work out the period of that beating, perhaps I'll demonstrate it to you first, and then we'll come back to this equation. Now, to demonstrate it, I've got a little application here. So this is my tone generator that I used a couple of weeks ago. So that's 256 hertz. And I'm going to apply another thing. If I apply 256, it gets a bit louder. But what I'm going to do is I'm going to actually apply 258 hertz. So the omega naught and omega are close. Let's assume 256 is omega naught, the natural frequency of the system, and 258 is the forcing function. You get beating, okay? So you can see at some points it reinforces, you get a loud noise, and other points it cancels each other out. We can reduce this to 257 if you want. So you can see it's reinforcing and then cancelling out, which is what's happening. Yeah, so that's a demonstration of it. That frequency of that woo sound, you can work it out. We've got omega minus omega naught, and the absolute value of that, so the positive value of that term, we can denote as delta omega naught, delta omega. And obviously to convert that into hertz, we can multiply that by 2, that equals 2 pi times by the value in hertz, gives you that. And if we delta f, we'll call that the frequency of the beating. Now, to work out the period of that beating, obviously you take 1 over f beat, so it's 2 pi divided by omega minus omega naught. Now, in that case that we looked at, the example that we just looked at, we had 257 hertz and 256 hertz. So this value, delta f, was 1 hertz. And so the period of beating was 1 second. So if I go back to that very quickly, that was 256, 257, that beating frequency, yeah, that's 1 second. And if I made this 258 hertz, obviously this delta f, so it becomes 2 hertz, so we get 1 over 2, so we should have half a second for the period. Yep. And obviously as you increase this, the frequency becomes so much higher. Oops. Yep. So obviously that's going to be, what, 40 44 hertz down here, so it's 1 over 44. So that's and obviously as you increase it even further, you just end up getting, you just get two tones, a chord essentially. And then if you were to plot that graph, so that equation where omega and omega naught are very close to each other, you get something that looks like this. In this case it's oscillating around 0, okay? And you get a point where it's reinforcing each other, so the amplitude is 2 times that amplitude in the equation. But then you also get times where it cancels each other out and you end up getting 0. Okay? So that's what's going on. That's the sound wave, 256 hertz and 257 hertz. You get this sort of thing going on, this beating effect. And that T beat, the period of beating, we can find from the equation.